The National Electrical Code, or NEC, does not specifically list running amps for written pole motors. Written pole motors are not exactly new, but more of a variation within the family of synchronous motors. Synchronous motors themselves are listed in the NEC, but their specific running amp values are not called out individually. The reason for this is that synchronous motors often find their use in large industrial settings, and therefore the running amps can fluctuate significantly depending on the requirements of each specific application. To determine the running amps of a written pole motor, there are several accepted methods. Firstly, you could use a motor nameplate calculator. Secondly, you could use a clamp-on ammeter. If determining the running amps of a written pole motor is proving difficult or uncertain, it's best to seek advice from a qualified electrician. Let's talk more about the NEC and how it relates to motors in general. Motors, as inductive loads, require special considerations in electrical installations, and the NEC provides guidelines to ensure safety and proper operation. Article 430 of the NEC is entirely dedicated to motors, motor circuits, and controllers. It covers a wide range of topics including motor circuit conductors, overload protection, short circuit and ground fault protection, motor control circuits, and motor disconnecting means. The NEC specifies requirements for conductor sizing based on the motor's full load current, which is the current the motor draws when operating at its rated horsepower and voltage. This full load current is used to determine the ampacity of the conductors supplying the motor. NEC Table 430.248 and Table 430.250 provide full load currents for alternating current, or AC, single-phase and three-phase motors, respectively. While these tables don't list written pole motors specifically, they offer a starting point for understanding typical motor current draws. Overload protection is essential to protect the motor from damage due to excessive current draw caused by overloads or stalled rotor conditions. The NEC requires overload protection devices, such as thermal overloads or electronic overload relays, to be sized appropriately based on the motor's nameplate current rating. These devices are designed to trip and disconnect the motor from the power supply if the current exceeds a predetermined level for a specified time. Short circuit and ground fault protection is necessary to protect the motor circuit from high fault currents that can occur during short circuits or ground faults. The NEC specifies the type and size of overcurrent protection devices, such as fuses or circuit breakers, to be used in motor circuits. These devices must be capable of interrupting the maximum available fault current at the motor terminals. Motor control circuits involve the control and operation of motors using control devices such as push-button switches, relays, and programmable logic controllers, or PLCs. The NEC provides requirements for motor control circuit wiring, overcurrent protection, and disconnecting means. Motor disconnecting means are required to provide a safe means of disconnecting the motor from the power supply for maintenance or repair purposes. The NEC specifies the type and location of disconnecting means, which must be readily accessible and capable of being locked in the open position. Branding is critical for motor installations to provide a low impedance path for fault currents to return to the source, minimizing the risk of electric shock and equipment damage. The NEC requires motor frames and enclosures to be grounded in accordance with Article 250. For synchronous motors, including written pole motors, the NEC provides additional guidance in Article 430 Part X, which covers synchronous motors and generators. This part addresses specific requirements for synchronous motor control, protection, and operation. Given that written pole motors aren't explicitly listed with running amps in the NEC tables, alternative methods for determining the current draw are necessary. Firstly, using a motor nameplate calculator can provide an estimate based on the motor's horsepower, voltage, and efficiency. Secondly, a clamp-on ammeter can measure the actual current flowing through the motor conductors during operation. Consulting with a qualified electrician is recommended when uncertainty exists regarding the correct approach or interpretation of NEC requirements. They can offer expertise in motor installations, NEC compliance, and safety practices. Let's discuss motor nameplate information and how it can be used to determine motor characteristics. A motor nameplate is a metal or plastic plate attached to the motor that provides essential information about its performance and operating characteristics. Key data found on the nameplate includes the motor's horsepower, voltage, full load amps, frequency, speed, insulation class, and service factor. The horsepower rating indicates the motor's mechanical power output capability. The voltage rating specifies the required supply voltage for proper motor operation, such as 208 volts, 230 volts, 460 volts, or 480 volts. The full load amps, or FLA, rating indicates the current the motor draws when operating at its rated horsepower and voltage. The frequency rating specifies the frequency of the AC power supply required for the motor, typically 60 Hz in North America. The speed rating indicates the motor's rotational speed in revolutions per minute, or RPM, at full load. The insulation class indicates the temperature rating of the motor's insulation system, which determines its ability to withstand heat without degrading. The service factor indicates the amount of overload the motor can handle for a short period without causing damage. Motor nameplate calculators are tools that use the information from the motor nameplate to estimate various motor parameters such as full load current, starting current, and torque. These calculators can be found online or in electrical engineering software. When using a motor nameplate calculator, it's important to input accurate data from the motor nameplate to obtain reliable results. The calculator typically requires information such as horsepower, voltage, frequency, and efficiency. The calculator uses these inputs to estimate the motor's full load current, which is the current the motor draws when operating at its rated horsepower and voltage. The full load current is used to determine the ampacity of the conductors supplying the motor and the sizing of overload protection devices. The calculator can also estimate the motor's starting current, which is the current the motor draws when it's first started. The starting current is typically much higher than the full load current and can cause voltage dips in the electrical system. The calculator can also estimate the motor's torque, which is the rotational force the motor produces. Torque is an important parameter for applications that require high starting or accelerating forces. Using a clamp-on ammeter to measure motor current is a practical method for determining the actual current flowing through the motor conductors during operation. A clamp-on ammeter, also known as a clamp meter, is a handheld electrical test tool that measures the current flowing through a conductor without requiring direct contact with the conductor. The ammeter is a clamp that can be opened and closed around the conductor to measure the magnetic field generated by the current flow. The ammeter then converts the magnetic field reading into current measurement displayed on the meter screen. When using a clamp-on ammeter to measure motor current, it's important to follow safety precautions and use the meter correctly. Firstly, ensure that the meter is properly calibrated and in good working condition. Secondly, select the appropriate current range on the meter to match the expected current level. Thirdly, clamp the ammeter around only one conductor at a time to obtain an accurate reading. To measure the current flowing through a motor conductor, identify the conductor to be measured, such as one of the phase conductors supplying the motor. Open the clamp of the ammeter and position it around the conductor, ensuring that the conductor is fully enclosed within the clamp. Close the clamp securely and observe the current reading displayed on the meter screen. The reading indicates the amount of current flowing through the conductor at that moment. It's important to take multiple readings over a period to capture variations in the motor's current draw due to load changes or operating conditions. Compare the measured current reading with the motor's nameplate full load amps rating to assess whether the motor is operating within its specified limits. If the measured current exceeds the nameplate rating, it may indicate an overload condition or a problem with the motor. Consult with a qualified electrician to investigate the issue and take corrective action. Let's delve into the standards provided by the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA, and how they relate to motor performance and testing. IEE Standard 112 is a widely recognized standard for testing and evaluating the performance of electric motors. It provides detailed procedures for measuring various motor parameters such as efficiency, power factor, and temperature rise. The standard specifies the test methods, instrumentation, and data analysis techniques required to obtain accurate and repeatable results. IEE Standard 112 covers a wide range of motor types, including induction motors, synchronous motors, and direct current, or DC, motors. It provides guidelines for conducting tests under various operating conditions such as no load, rated load, and overload. The standard also includes procedures for correcting test data to account for variations in ambient temperature and supply voltage. The test methods described in IEE Standard 112 include direct methods, which involve measuring the motor's input power and output power directly, and indirect methods, which involve calculating the motor's efficiency based on measurements of other parameters, such as voltage, current, and speed. The standard also specifies the instrumentation requirements for conducting motor tests, including wattmeters, ammeters, voltmeters, and thermocouples. The instrumentation must be calibrated and accurate to ensure the reliability of the test results. NEC Standard MG-1 is a widely used standard for motor construction, performance, and testing. It provides guidelines for motor manufacturers and users to ensure that motors meet certain performance and safety requirements. NEC Standard MG-1 covers a wide range of motor types, including induction motors, synchronous motors, and DC motors. It specifies the mechanical and electrical characteristics of motors, such as frame sizes, enclosure types, and installation classes. The standard also includes requirements for motor testing, including performance tests, temperature rise tests, and vibration tests. NEC Standard MG-1 defines the standard frame sizes for motors, which ensure interchangeability between motors from different manufacturers. The standard also specifies the enclosure types for motors, such as open drip proof, totally enclosed fan-cooled, and explosion proof. These enclosure types provide different levels of protection against environmental factors such as moisture, dust, and hazardous gases. The insulation class is specified in NEC Standard MG-1 define the maximum allowable operating temperature for the motor's insulation system. The insulation class determines the motor's ability to withstand heat without degrading. The standard also includes requirements for motor testing, including performance tests, temperature rise tests, and vibration tests. These tests are performed to verify that the motor meets the specified performance and safety requirements. When working with motors, it's important to consider power quality issues and their impact on motor performance and reliability. Power quality refers to the characteristics of the electrical power supply, including voltage, frequency, and waveform. Poor power quality can lead to various problems such as voltage sags, voltage swells, harmonics, and transients. Voltage sags are temporary reductions in voltage that can cause motors to slow down or stall. Voltage swells are temporary increases in voltage that can damage motor insulation and electronic components. Harmonics are distortions in the voltage and current waveforms that can cause motors to overheat and lose efficiency. Transients are sudden, short-duration spikes in voltage that can damage motor insulation and electronic components. To mitigate power quality issues in motor installations, several measures can be taken. Firstly, ensure that the electrical system is properly grounded and bonded to provide a low impedance path for fault currents. Secondly, use surge protection devices to protect motors from voltage transients caused by lightning strikes or switching events. Thirdly, install harmonic filters to reduce harmonic distortion in the electrical system. Fourthly, use constant voltage transformers, or CVTs, or voltage regulators to stabilize voltage fluctuations and maintain a consistent supply voltage to the motors. Maintaining motors properly is essential for ensuring their reliable operation and extending their lifespan. Regular maintenance tasks include inspecting motor windings for damage, lubricating bearings, cleaning motor surfaces, and tightening electrical connections. Motor windings should be inspected for signs of overheating, insulation damage, or contamination. Bearings should be lubricated regularly to reduce friction and prevent wear. Motor surfaces should be cleaned to remove dirt, dust, and debris that can impede cooling. Electrical connections should be tightened to prevent loose connections, which can cause overheating and voltage drops. In addition to regular maintenance, motors should be tested periodically to assess their performance and identify potential problems. Motor testing can include insulation resistance tests, winding resistance tests, and vibration analysis. Insulation resistance tests measure the resistance of the motor's insulation system to ground, which can indicate insulation degradation. Winding resistance tests measure the resistance of the motor's windings, which can indicate shorts or open circuits. Vibration analysis measures the vibration levels of the motor, which can indicate bearing problems, imbalance, or misalignment. When installing motors, it's important to follow proper installation practices to ensure their reliable operation and prevent premature failure. Firstly, ensure that the motor is properly aligned with the driven equipment to minimize stress on the motor bearings and shaft. Secondly, use flexible couplings to absorb vibration and misalignment between the motor and the driven equipment. Thirdly, provide adequate ventilation to prevent overheating. Fourthly, protect motors from exposure to harsh environmental conditions such as moisture, dust, and corrosive chemicals. In conclusion, determining the running amps of a retin pole motor involves considering various factors and utilizing appropriate resources. While the NEC doesn't explicitly list running amps for these motors, understanding the principles of motor operation, consulting motor nameplate information, and utilizing tools like clamp-on ammeters and motor nameplate calculators can aid in determining the correct values. Consulting with a qualified electrician ensures compliance with safety standards and best practices. Also, consider IEE and NEMA standards for performance and testing.